It was a locomotive designed to be weak on purpose, not slow by accident, not small because engineers failed, but deliberately capped at exactly 44 tons, not a single pound more. In an era obsessed with horsepower and size, General Electric built a machine that refused to grow stronger, and that decision saved hundreds of railroads from collapse. This locomotive did not conquer mountains or pull record-breaking trains. Instead, it obeyed a line of text buried inside a labor contract. One rule, one number, and an entire machine built around it. Why would engineers design power around a law instead of physics? And what happened when the law finally changed? In the United States of the 1930 seconds and early 1940 seconds, railroads were not just fighting geography or competition, they were fighting math, and the most dangerous numbers were not grades or tonnage. They were written in labor agreements. For decades, American railroad unions had negotiated strict rules about crew size. Steam locomotives always required at least 2 people, an engineer and a fireman. When diesel power arrived, railroads hoped it would finally reduce labor costs. But the contracts adapted. A critical threshold emerged quietly and decisively. Any locomotive weighing more than 90,000 pounds required 2 operators. Any locomotive at or below that limit could legally be run by 1 person. 90,000 pounds, 44 tons. To a major railroad, the difference between 1 crew member and 2 was annoying. To a small railroad or an industrial plant, it was existential. Switching yards at steel mills, ports, refineries, and factories ran on thin margins. Paying a second operator on every shift could erase profits entirely. Many short lines faced a brutal choice. Keep aging steam locomotives and pay full crews. Buy diesel and still pay full crews, or shut down. The Great Depression had already wiped out hundreds of marginal railroads. World War II increased industrial output, but also froze labor rules in place. Steel mills ran day and night. Ports moved mountains of freight, but every switching move still carried the same labor cost burden. Efficiency was strangled not by technology, but by contracts written to protect jobs in an older era. General Electric watched this crisis closely. Unlike competitors focused on big road diesels, GE saw an opening at the bottom of the market. Not a glamorous one, not a powerful one, but a market defined by survival. If a locomotive could stay under the magic weight limit, it could operate with a single engineer. Over a decade, that difference meant thousands of dollars saved per locomotive. Over an entire fleet, it meant staying alive. This was not theoretical. Internal studies showed that labor costs could exceed fuel and maintenance combined for industrial operators. A machine that saved horsepower but cut crew size in half would win every time. The constraint was absolute. Go 1 pound over 44 tons and the advantage vanished instantly. The crisis was not about pulling more cars. It was about pulling fewer invoices. At the same time, industrial customers did not need speed or range. They needed torque at walking pace. They needed reliability. They needed something that could start, stop, reverse all day without breaking down. And above all, they needed to avoid triggering the second crew requirement. This was the environment that shaped the GE 44-ton switcher. It was not born from ambition. It was born from pressure. Law boxed in engineering, economics narrowed every option. And inside that shrinking space, General Electric had to design a machine that was strong enough to work, yet weak enough to stay legal. So who actually controlled the design of this locomotive? The engineers at GE, or the words written into a labor contract decades earlier? BT Tree. At the center of this story was not a single visionary inventor or a famous railroad executive. It was an engineering culture shaped by constraint. Inside General Electric, teams at the Erie, Pennsylvania works were used to building massive machines. Turbines, generators, electric locomotives. Power was their language. But the 44-ton problem demanded the opposite instinct. The motivation came from customers most manufacturers ignored. Small, short-line railroads, steel mills with private tracks, ports, refineries, military depots. These operators were not asking for innovation. They were asking for relief. They wanted a machine that fit through a legal loophole. 1 operator instead of 2. 1 paycheck instead of 2. That single change could determine whether a plant rail system survived the next decade. GE sales engineers became translators between law and metal. They carried labor contracts into design meetings. They treated the 90,000-pound limit as sacred, not a guideline, a cliff. 1 pound over, and the entire economic argument collapsed. This was not a locomotive designed for pride or prestige. It was designed for accountants. On the other side were the unions. They did not oppose safety. They opposed erosion. The single operator rule existed to protect jobs in an age when automation threatened everything from firemen to brakemen. From their perspective, weight was an objective standard, easy to enforce, easy to inspect. If manufacturers wanted to cut crews, they would have to cut steel first. Railroad managers stood in the middle. Many privately admitted the rule made no mechanical sense for diesel switchers. A diesel did not need a fireman. It did not need constant tending. But challenging labor agreements was risky. Strikes could shut down entire regions. The safer path was to comply rather than confront. That compliance shaped every decision. Engineers were told to forget growth margins, forget future upgrades, forget over-engineering. Every component had to justify its weight. Frames, trucks, engines, cooling systems, electrical gear. If something could be smaller, it had to be smaller. If it could be lighter, it had to be lighter. Reliability could not come from mass. It had to come from balance. The result was a strange alignment of incentives. Engineers trying to remove pounds, managers trying to remove wages, unions trying to preserve jobs, and customers desperate enough to accept a machine that would never be powerful, never be fast, and never be impressive on paper. This was not innovation driven by dreams of the future. It was innovation driven by the fear of shutdown, and that fear gave the 44-ton switcher its true designer, not a person, but a system. So how do you build a locomotive that obeys a contract more strictly than the laws of physics? The solution began with a rejection of conventional thinking. Most diesel switchers of the era relied on a single large prime mover, one engine, one generator, one heavy block of metal concentrated in the center of the frame. That approach was simple and proven. It was also impossible under the 44-ton limit. A single engine powerful enough to do real switching work would push the locomotive past the legal threshold instantly. The weight of the engine itself was only the beginning. Cooling systems, generators, frames, and reinforced trucks followed. The math did not work, so GE split the problem in half. Instead of one large engine, engineers selected two smaller diesel engines. Each engine drove its own generator. Together, they produced enough power for industrial switching, but individually, they stayed light enough to be distributed across the frame. Weight was no longer concentrated. It was spread. This decision defined the entire locomotive. The twin-engine layout allowed the frame to remain shorter and lighter. It also introduced redundancy. If one engine failed, the locomotive could still limp home on the other. That feature was not advertised as innovation. It was marketed as reliability. In industrial service, uptime mattered more than speed or horsepower. Every structural choice followed the same logic. The frame was built strong enough to survive constant starts and stops, but not strong enough to waste steel. Trucks were carefully designed to distribute axle loads below inspection thresholds. Axle load was just as critical as total weight. Inspectors did not only weigh locomotives, they measured pressure on the rails. The cab was compact, not cramped, but efficient. There was no wasted volume. Controls were arranged for one operator because that was the entire point of the machine. No accommodations for a second crew member, no extra seat, no redundancy in human terms. Cooling systems were trimmed to match duty cycles. This locomotive was never expected to run at full power for hours. It would work in bursts. Push cut, stop, reverse, repeat. Everything was sized for that reality. Oversizing meant extra weight. Extra weight meant an extra paycheck. Even fuel capacity was calculated carefully. Enough for a full shift. Not enough for long road runs. This was not a locomotive that roamed. It lived inside fences, ports, mills, yards, bases. Its world was measured in hundreds of meters, not hundreds of miles. The final figure mattered more than any performance specification. 88,000 pounds, just under the limit, not a rounding error, a margin of survival. Engineers knew that where paint modifications and dirt would add weight over time. The design had to stay legal even after years of service. The result was a machine that looked unremarkable, boxy, short, almost conservative. But beneath that simplicity was an extreme form of optimization, not for power, not for speed, but for legality. The 44-ton switcher was not designed to be the best locomotive. It was designed to be the most compliant locomotive possible. And then came the moment that mattered most. The first time it moved under its own power. The first time inspectors checked the scales. The first time a railroad realized it could fire up a diesel with only one name on the payroll. Would it actually work in the real world? Or would this carefully balanced design collapse the moment steel met rail? Production began at the General Electric Works in Erie, Pennsylvania, a facility more accustomed to building machines that pushed limits rather than obeyed them. For the engineers and shop crews, the 44-ton switcher felt almost unnatural. Every build began with a scale in mind. Weight was tracked obsessively. Steel thickness, wiring length, component placement. Nothing was casual. Unlike larger locomotives, there was no room for future growth, no allowance for upgrades. If a component solved a problem but added unnecessary mass, it was rejected. Assemblers were instructed to think like inspectors. What would be measured? What would be questioned? What would fail a check? The twin-engine arrangement complicated production. 2 engines meant twice the alignment, worked twice the fuel and cooling connections, and twice the electrical integration. But it also allowed smaller, lighter parts that could be handled more easily on the shop floor. In a strange way, building 2 modest systems proved simpler than wrestling one oversized machine into compliance. Early units rolled out with cautious optimism. They were not sent to mainline railroads, they were sent to places where failure would not make headlines. Steel mills, industrial yards, dockside tracks. Customers who needed switching done quietly and cheaply. Testing focused on the work the locomotive was actually built for. Low-speed torque, repeated starts under load, tight curves, short moves, stop and reverse cycles that would destroy clutches and transmissions in lesser machines. Engineers watched temperatures closely. Overheating would require heavier cooling. Heavier cooling would break the design. The first runs revealed a machine that felt different from anything else in the yard. The twin engines produced a distinct rhythm. Not a deep, continuous growl, but a paired mechanical pulse. Operators noticed the vibration immediately. It was not violent, it was persistent. A reminder that this was a compromise machine doing exactly what it was designed to do. Performance was modest, but adequate. The 44-ton switcher could not shove long cuts of cars like heavier switchers, but it did not need to. In industrial service, cuts were shorter and moves were frequent. Where a larger locomotive wasted power idling, this one worked efficiently within its narrow envelope. Inspectors were the real test. Locomotives were weighed, axle loads were measured, documentation was reviewed, and again, the numbers held. Under the threshold, 1 operator, no fireman required, no second engineer demanded. That moment changed the conversation. Customers who had hesitated began placing orders, not because the locomotive was impressive, but because it was legal. It solved a problem no one else had bothered to solve properly. Field reports returned to Erie. Crews praised the simplicity. Maintenance staff appreciated the redundancy. If one engine went down, the other often kept operations moving until repairs could be scheduled. In facilities where downtime meant halted production, that alone justified the purchase. There were issues. Cold weather starts were challenging with smaller engines. Traction was limited. On slick rail, the lightweight design showed its weakness, but these were accepted trade-offs. The locomotive was not meant to be perfect. It was meant to survive within a rule. By the time the first production run was complete, the verdict was clear. The 44-ton switcher did exactly what it promised. It worked, it stayed under weight, and it allowed one person to do a job that had required 2 for generations. But success built on constraints is always fragile. What happens when conditions change? What happens when the law that shaped the machine begins to loosen? The 44-ton switcher spread quietly. There were no dramatic unveiling ceremonies and no glossy advertisements promising a new era of railroading. Instead, the locomotive appeared where survival mattered more than image. Inside steel mills where molten metal glowed at night, along docks where ships unloaded around the clock, inside refineries, ports, warehouses, and military depots where rail lines existed for one reason only: to keep material moving. Orders came steadily. not from giants but from dozens of small operators. Over time, more than 300 units were built. Each one represented a calculation. One locomotive, one operator. Thousands of dollars saved every year. In industries measured by margins rather than miles, that math was irresistible. The 44-ton switcher proved especially valuable in environments that punished machines. Tight curves, abrasive dust, uneven track, constant reversing. Larger road switches were often overkill and underutilized. They burned fuel idling. They wore components unnecessarily. The GE machine fit its environment like a tool designed for one job and nothing else. Its limitations became part of its identity. Crews learned not to ask too much of it. Shortcuts only. Steady movements. Respect the traction limits. In return, it delivered predictability. Day after day, shift after shift, it did not chase schedules. It simply worked. In ports and industrial complexes, something else happened. Managers noticed how rarely the locomotive stopped operations entirely. The twin-engine design meant failures were often partial rather than total. One engine down did not always mean a shutdown. That resilience mattered more than raw power. During World War II and the years that followed, the locomotive found another role. Military bases and government facilities valued the same qualities as industry: simplicity, reliability, and compliance. Crew rules mattered even more under wartime labor pressures. The 44-ton switcher fit seamlessly into restricted environments where manpower was precious. For a brief window, it became the default answer to a specific question: how do you move cars legally with one person? No other locomotive answered that question as cleanly. Yet its success was always conditional. It depended on the rule remaining unchanged. It depended on customers accepting limited performance. It depended on a narrow definition of value. As larger road switches grew more flexible and labor agreements slowly evolved, the edges of that window began to blur. Operators started asking harder questions. What if a heavier locomotive could do more with only slightly higher costs? What if the law no longer enforced the same thresholds? The 44-ton switcher had won its battle, but it was never meant to win a war. So what happens to a machine designed around a single rule when that rule begins to lose its grip? The decline of the 44-ton switcher did not arrive as a failure. It arrived as a shift. Slowly and quietly, the conditions that had made the locomotive indispensable began to loosen. Labor agreements changed. Over time, railroads negotiated more flexible crew rules for diesel locomotives. The strict weight threshold that once defined everything began to matter less. A heavier locomotive no longer guaranteed a second crew member. And once that connection weakened, the 44-ton switcher lost its primary advantage overnight. At the same time, diesel technology improved rapidly. Road switchers became more versatile. One locomotive could switch yards, handle industrial work, and still run on branch lines. For many operators, consolidation made sense. Why maintain a specialized machine when a single heavier unit could do everything with similar labor costs? The 44-ton switcher suddenly looked narrow. Its carefully engineered limits became liabilities. It could not grow into new roles. It could not pull longer cuts. It could not adapt to changing expectations. The very discipline that had once saved it now trapped it. Some units continued working quietly for decades in private industrial service. Inside mills and plants where rules changed slowly and tasks remained constant, the locomotive still made sense. Others were sold second-hand. Some were stripped for parts. Many were scrapped without ceremony. They were not famous machines. Few people noticed when they disappeared. Yet, a surprising number survived. Museums and historical societies recognized the 44-ton switcher as something unusual, not because of what it could do, but because of why it existed. It represented a moment when law, economics, and engineering collided with absolute precision. Preserved examples now sit on short sections of track, paint faded, engines silent, but the story intact. The consequences extended beyond preservation. The 44-ton switcher became a case study in constraint-driven design. It showed that optimization does not always chase maximum performance. Sometimes it chases minimum compliance. It proved that machines can be shaped as much by contracts as by physics. For General Electric, the locomotive marked a different way of thinking. Success did not always mean dominating the top of the market. Sometimes it meant owning a narrow space no one else wanted to occupy. For railroads and industry, it left a quieter lesson. Systems built around rigid rules create equally rigid machines. When the rules change, those machines may have nowhere to go. The 44-ton switcher was never obsolete in the traditional sense. It simply outlived the problem it was designed to solve. And that raises the final question. What does this machine really teach us about progress, efficiency, and the hidden forces that shape engineering decisions? The GE 44-ton switcher was not born from ambition. It was born from pressure, from a single line in a labor agreement, from an economic reality where one extra worker could decide whether a railroad survived or vanished. Engineers did not ask how powerful the locomotive should be. They asked how light it had to remain. That question shaped everything. This machine reminds us that engineering does not exist in isolation. Steel responds to more than stress and heat. It responds to law, to contracts, to economics. The 44-ton switcher obeyed rules written by people who never touched a throttle. Yet, those rules dictated its frame, its engines, and its limits more completely than any physical equation. For a time, the design was perfect. It solved the problem exactly as defined. No more, no less. When the definition changed, perfection became confinement. The locomotive did not fail. The world around it moved on. There is a temptation to judge machines only by what they achieve in absolute terms: horsepower, speed, size. By those measures, the 44-ton switcher seems forgettable. But judged by its purpose, it was extraordinary. It kept small railroads alive. It kept factories moving. It turned legal compliance into mechanical advantage. Its story carries a lesson far beyond railroading. Innovation is not always about breaking limits. Sometimes it is about respecting them so precisely that they become tools. Constraints do not always block progress. They can define it. If you were an engineer in that moment, would you have built something stronger and risked everything? Or would you have done what GE did and built exactly what the system allowed? The next time a machine seems underpowered or compromised, it may be worth asking a different question. What invisible forces shaped it, and what problem was it truly designed to solve?